Hello everyone, welcome to lecture 5 of this Gyan lecture series. To recap what we have been discussing in the previous lecture, so we talked about 4F imaging systems, and the basic concept here is that if you have an object in one plane, and there is something called a Fourier plane at a distance 2F, and then when there is a lens in between, and then you have put another lens at a distance 2F. From that you have an image, and you have control over the Fourier transform of the object in this particular plane, and we can, by manipulating the Fourier plane, we can build different kinds of imaging systems. That's the essence of what we discussed last time. And there is the input output. You can think of it as a linear system where you can choose the Fourier coefficients, and the transfer function of the system is in your control, and that way you can build new kinds of imaging systems. And one of the examples of a kind of system where you can use space is what's called holography. And I gave you a few examples of different kinds of holography. But the main idea here is that you have an object, and you have a reference a beam of light. You interfere the two in on something which is photosensitive to create what's called a holographic plate. And if you have the reference beam incident on this holographic plate, then light comes out at the other end. And importantly, the shape of this wavefront is such that if you look from this side and observe the wavefront, if you look at the light that comes there, it will look like as though the object is actually present here. If the object was here and there was no holographic plate, then whatever light trace comes there, that is exactly what you would see, and therefore the object will look like 3D. It will have the same shape and feel and structure of 3D object, and so holography gives you kind of the appearance of a three-dimensional structure of an object, or three-dimensional shape of an object. The other thing we discussed was a kind of microscopy or an imaging system called quantitative phase imaging, which is an extension of what's called phase contrast microscopy, where you quantify the phase. And last time we saw how this imaging system works. It uses one of the constructions uses a 4F imaging principle, and then you do phase shifting in different ways, and so you can get very precise thickness measurements at a nanometer scale, and that happens to be very important for a bunch of diseases, and so it can be useful for different kinds of disease analysis. Any questions about anything we discussed last time? Okay. Okay, so today we will discuss light matter interaction. So the question that we are trying to answer is, what happens when light interacts with matter? What are the different possibilities, and what, like in each of these situations, what to do about the light? Like how does light behave when it goes through some material, some object, and from making a measurement of the light that comes back, can you understand something of what is going inside the what is going on inside the object? That's basically the topic of today's discussion. So if a wave of light, let's consider a plane wave, comes in and is incident on an object, there are several different things that can happen. Okay, so one is it could get reflected from the surface. So reflection can happen from the top surface, and then, or refraction, light could bend and go inside. And this is not just true for glass. This is true for any surface, even if it is like say tissue or anything else of that for that matter. Even complicated kind of objects and samples can also have reflection and refraction, and combination of multiple things going on at the same time. Okay, and so light is incident, reflect. It can reflect, it can refract, it can, after like if there is an aperture or if there is some obstruction of some sort, it can diffract. So So you have a diffracted wave coming out, for example, or when it goes through, it can scatter. There may be something in the on the inside of the object where because of which it scatters, and light can get absorbed as well as it travels. So there are all these different phenomena that can happen. We'll go through one by one all the different kind of things that happen, and kind of each one of these. The reason this is important is that every single one of these phenomena, whether it's a reflection or refraction or diffraction or scattering or absorption, can be used to build some kind of an imaging system, and often something which is medically, clinically, biomedically useful. Okay, so we study each of these phenomena, always keep in the back of your mind that there is something you can build out of this which is useful. Okay, so we'll go through the kind of details and mathematical details of how exactly each of these phenomena work, and correspondingly how to build instruments with this with each of these approaches. Okay, and to kind of give some basic kind of assumptions that we are using. So typically we assume that a wave has a certain lambda wavelength. It's traveling, which has a field which is described this way, which is going in the z direction. So that is in optics, it's a reasonable and general assumption that light is traveling along the z direction and the xy is the kind of lateral plane. Okay, and whenever there is a time shift, there is also a phase shift, and a certain distance delta v corresponds to a certain time delay or a phase delay or a distance delay. Okay, so there is a so you have a light wave, and the shift in the light wave as it travels results in a phase shift. Similarly, if you have a wave, instead of going along the z direction, the direction of a wave is given by the k vector. So it is k vector, and it tells you it's a vector which tells you the direction of the plane wave, and it also has a wavelength lambda, which is shown here, and it is traveling in a certain direction, and e to the I or minus j k dot r. Okay, r is xyz, k is the direction vector, tells you it's a plane wave going in a particular direction. That's a way to kind of express a plane wave. This kind of a plane wave can be given by an equation of this form. Okay, now the next question is, how does light travel? Like we saw a little bit of this in the previous class. If so, here is a general equation for how you can find the shape of the wave for any given wave. Okay, let's say you have like, so you can think of any general wave shape as consisting as a summation of a linear combination of plane waves, or linear superposition of plane waves. And so so there are multiple. So you have plane wave in this direction, and a plane wave in this direction, and a plane wave in this direction, plus a plane wave in this direction. So you add up the contribution. Sorry, can you see this from far away? Yeah, okay. So if you add up the contribution of all these plane waves, you will get something that has some specific shape. So any shape of wavefront can be thought of as a combination of these plane waves. The question is, how much of each of these plane waves? What is the amount of each plane wave you need to add to construct this shape? And that amount are called the Fourier coefficients. So maybe you use 1 unit of this plus 0.5 of this plus 1.5 of this plus 10 of this. So you add up the weighted average, a weighted sum of all these plane waves gives you a overall wavefront. And this weighted sum is essentially a Fourier transform. And therefore, what you have is so the f of kx ky in this equation here tells you how much of each plane wave. So this essentially describes a plane wave. You can notice that this is of the form e to the minus j k dot r, right? What is k dot r? It's kxx plus kyy plus kzz. So that's exactly what we have here. So k dot r equals, yes. So for each of these plane waves in the direction k, you take the weight of that and weight times this, add up all the different plane waves. Addition is just integration, right? Like repeated addition of different small pieces. Integration is just addition of small pieces, and that's so take different plane waves, have a certain weightage, and add them all up. You get the overall field at any given position. That's the essence of how you think about this. Although this equation looks like something, the meaning, like if you understand and interpret it, it becomes fairly simple to read. Okay, and additionally, how can you find because when you have integrals, you have initial conditions, right? Like you need boundary conditions or initial conditions, otherwise you can't. There's something missing from. So therefore, one way to have a boundary condition is at z equal to 0, at some starting point, if you know the field, then at any other position, you can figure out the field using this equation. So put z equal to 0 in here. What you get is, like in this case, the z here, this particular term will become 0. So this will be kxx plus kyy. And if you look at this is a Fourier transform, essentially a simple Fourier transform relationship. Okay, so you have the field here, and field at any other point you can use by figure out by using this kind of an equation. Any questions about this? Okay. Yeah. So next, let's get to how you think about spherical waves. I mentioned plane waves, right? You think of it as a summation of plane waves. Another way of thinking about wave optics is as a combination of spherical waves. And let's think through how exactly to do that. Okay, so that's the next thing I'll discuss. So if you think of a point here which is emitting light in all directions, it sends out a spherical wave in all different directions, and the field here at a location r, right? Like you have a point, you have a point r here, and this is in the xyz kind of plane, and the field at this point, and this is a scalar field. Notice that we are doing a scalar kind of scalar, meaning it's not a vector, it's a number. At any given point there is a number, the field corresponds to one number. Okay, it's a vector will have 3 numbers associated at any given point, and scalar has one number. Okay? So what happens is that if light wave is generated at the origin of coordinates, then the field at that position r is a0 divided by r. This is small r, so this is r here is basically magnitude of the vector r, which is rx square plus or x square plus y square plus z square square root. Okay, so that's the value of r. Sorry, I didn't write this properly, but yeah. So x square plus y square plus z square square root. So that's this r term here. So as it travels far away, there is a decay, there is a reduction in its value, and then not only that, it accumulates phase. And how much phase does it accumulate? If it travels a distance r, then e to the j k times r. So k times r, or so how do you think about this? One intuitive way to think about this is let's think of k equals 2 pi by lambda, let's say in air. Okay, so this k dot r, k times r is 2 pi, so k times r is 2 pi by lambda times r. Okay, so this is 2 pi times r by lambda. I'm just rearranging the terms. So it has traveled a certain distance that say corresponds to say 10 wavelengths. So r divided by lambda is how many wavelengths of distance has the light traveled. So if it has traveled 10 wavelengths, so and each wavelength it accumulates a phase angle of 2 pi. So over 10 wavelengths it accumulates 2 pi times 10 radians of angle. That's the way to think about this. If it travels a certain distance, each wavelength, one lambda, it is corresponds to a 2 pi angle, and so 10 lambdas or 20 lambdas, it corresponds to 10 times 2 pi or 20 times 2 pi. That is the amount of angle phase that is accumulated from where it started to where it has reached. So that is what we mean by how much phase has accumulated from point A to B. So this is for any direction in spherical waves. That's how you interpret this particular equation. So let me erase some of this. Okay, so yeah, so that's, sorry, yeah, okay. So now the question is, this is just for one point which is emitting light from the origin of coordinates. What if that's not the case? Like, what if there are multiple points, or it's a combination of a large number of points and it is distributed, like not at the origin but in all different places? Then what you do is, let's say there is a position r prime, there is one point emitter at position r prime. Let's look at a distance r. So how do you find the field at a distance r? For the contribution of this at the position r prime, let's say it's emitting a spherical wave. So let me draw this. Okay, you have a point r prime, which is a vector, and then there is a point r here, which is another vector. Draw a line from here to here, right? So there's this. What's the distance here? It's r minus r prime magnitude. That's the distance that the wave has traveled. And so if you start from here, so what would be the amplitude at this point? Let's say this amplitude is, starting point is 1. What is the amplitude at the point r? 1 by, exactly, 1 divided by magnitude of r minus r prime, right? That's the amplitude. How much phase has it accumulated? Yes, e to the, so this corresponds to a certain distance. So if you think of e to the minus j k times r minus r prime, right? So that distance, so take this distance, multiply by k, e to the j k dot r, k times r minus r prime magnitude. This is the amount of phase, this is the amount of the amplitude. If you start from here, this is you can predict the field at this point using this expression. Not only that, you assume that if the value of the starting point is 1, the intensity of the field, or sorry, the value of the wave front emitted is 1. But if it's not 1, if it is, say, something like s, all you have to do is take this s of r prime is at this position r prime, the value of the field is like say s of r prime, and therefore the field at this position r is s of r prime divided by r minus r prime magnitude times e to the j times k r minus r prime. So this is how you, like, if you know the field at one point, you can predict the field at another point using this expression. So now what happens if instead of at one r prime, a different point and a different point and different point and different point, you want to add up the, so you want to find the contribution of sorry, at different at different values of r prime, for different values of r prime, what is the total field at the position r? For r prime, move the value of r prime, choose different values of r prime, add them all up, and you get the total contribution of the field, total field at this location. Right? How do you add up all the pieces? How all the dots? Each dot is emitting a spherical wave. Okay, so S of r prime, e to the j k r minus r prime divided by r minus r prime. Okay, so basically you add up, integrate. In other words, add them all up, and you get the field at a position r. That's the way you think about this. So what we are doing is take different points. For one point, there is emitting a spherical wave. Another point is emitting a spherical wave. Another point is emitting a spherical wave. Sorry, add up the fields, because of every one of these points is contributing something. Add up all the contributions. In other words, integrate, and you get your field at that point r. Okay, so that's how you construct. And so this is what's called the Fresnel-Huygens principle, and this is a quantitative way of figuring out the scalar field at one point given the field at another point. And this is in fact like how we can actually propagate light and kind of understand light in a lot of different situations. The next thing I wanted to talk about is, what if light is not just propagating in air, but is going through a medium, and not only that, it's going through a medium which is absorbing. Then what? So right now we saw, so in the previous example, we assumed it's going through air, right, or going through free space. So you can predict the field here if there is air in between, or there is nothing in between, vacuum in between. Then you can use this equation to make the prediction. The question then is, if it is not going through air, if it's actually going through some kind of a medium which absorbs some of the light, then how do you figure out how light propagates and travels through a medium? Okay, that is, in that case, what happens is basically damped waves, or damping, in other words. Okay, what it means is that you start with a certain wave intensity at the top. As it travels, some of the energy gets absorbed by the medium in such a way that as it travels, the intensity keeps becoming lesser and lesser and lesser as you go along. How much does it become less by? That is a matter of like what's called the absorption coefficient of that medium. In other words, it reduces in if you start with an intensity of say 1, it becomes smaller and smaller, and the point where it becomes 1 over E, for example, typically is kind of taken as the kind of absorption, like value of the absorption coefficient. So the way to mathematically kind of represent that is, instead of having a k vector which is real values, in the previous case k vector was just 2 pi by lambda or like something of that sort, right? But if instead of it being purely real values, if it is complex values, then the imaginary part of the k vector will tell you something about the absorption coefficient. That is really related to the absorption coefficient. So here is kind of the equation. So if k equals beta, which is the real part, minus j alpha divided by 2. That is alpha divided by 2 is because we are interested in intensity and not field. So I'll show you in just a minute. But basically there is a real part and there is an imaginary part. This alpha is related to the absorption coefficient. So if you the field at a position z equal to 0 is something, field at any given z is u0. u0 is the starting at z equal to 0, starting point, times e to the exponential of e to the alpha z divided by 2. So what all I'm saying is e to the I or k dot r, right? R is just nothing but z in this case, z and z vector. Okay, so in this case, if you just the light is just traveling along the z direction, that's the case I'm looking at. What do you have here? E to the minus j k z, and this one is e to the minus j k is beta minus j alpha by 2 z, right? So now bring the z inside, you will get e to the minus j beta z times e to the minus of minus that plus, then j square will again become a minus alpha by 2 z. Okay, so basically that's how you get to this e to the beta minus j beta z, which is this one, and e to the alpha divided by 2 z, which is this expression over here. U0 is the starting field. So that's how you get this expression over here. And so, and if you take the magnitude, so this is the field. So if you make a measurement of the field, you get the intensity. You take the magnitude square. What happens to this term when you take the magnitude square? Yeah, it becomes 1. So it is of the form e to the j theta, right? And you take the magnitude, it becomes 1. And so this term will disappear. And when you have a square, so that's where e to the minus alpha divided by 2z. So if you take the square of this, it's the same as e to the alpha z by 2 times 2. And therefore it will become e to the minus alpha z. And I0, U0 square is equal to I0, the starting intensity. So what you have in essence is the intensity at a position z is the starting intensity times an exponential reduction e to the minus alpha z. And so there is the light intensity is reducing exponentially as you go along. And how much it reduces by when z equal to 1, e to the minus, this is equal to e to the minus or alpha times z equal to 1, it will become 1 over e. So that's the definition of the absorption coefficient in a sense. Okay? So at what distance does this kind of fall to 1? Does the intensity? What is the rate of reduction of this intensity inside the like absorbing medium? Any questions about this? Okay, so this is essentially how you think about absorption of light, and so there are other very related things. So we'll use this. There is something called Beer-Lambert's law, which I'll get to in a few minutes. Yeah, so let me erase this a little bit. Sorry about that. Yeah. So if a certain amount of light is incident on the top surface, as it goes through, there is a reduction in intensity. It depends on the thickness of the sample, and it also depends on the absorption coefficient. This is used in what is called in spectroscopic imaging and spectroscopy and spectroscopic imaging in what's called Beer-Lambert's law to identify the absorption coefficient at any given wavelength. It turns out that different molecules absorb differently at different wavelengths. And in the mid-infrared, I'll dedicate a lot more time to this at a later time, but I just wanted to introduce why this is important and how this is useful. So this is at a single wavelength. So you can do it at wavelength 1, 2, 3, 4, and at a range of wavelengths. Maybe in the visible, maybe in the near infrared, maybe in the mid-infrared, maybe at any other wavelength. So if you make a measurement at a range of wavelengths and figure out the absorption coefficient at different wavelengths, then you can plot something like looks like this. say you measure the absorption coefficient as a function of wavelength, or more typically what you do is plot what's called inverse of wavelength, which is wave number. Okay, wave let's just call it 1 over lambda for now, and alpha. So you get a plot of this sort. Okay, something of this sort. At different wavelengths, you have different absorption values, and these peaks correspond. So each one of these peaks typically corresponds to some kind of say molecular bond. There is if a wavelength, light of some wavelength is incident on the molecular bond, maybe it's a carbon hydrogen bond or a carbon carbon bond, or like carbon oxygen bond or something of that sort, right? So for a one bond, it has a very specific absorption wavelength, and at that wavelength it absorbs light, and therefore there is a strong, the absorption coefficient is very large. At a different wavelength it doesn't have absorption. And when a molecule consists of a bunch of different bonds, so you will, for a single molecule, have multiple peaks at different wavelengths. And by looking at this profile of where all the different places where light is absorbed, you can figure out what molecule it is. This is essentially called spectroscopy. The measurement of light at different wavelengths and making a plot of it, and by using that plot to figure out what molecule would create this kind of a spectral profile. That is the reason why this kind of an absorption coefficient is useful and important. And so this is one of the ways by which you can identify some unknown chemical. For example, in forensics, like say people get something, some unknown chemical from a crime site, and they don't know what it is. They can put into an instrument which is called FTIR spectrometer or something. There are different kinds of instruments, but I'll explain some of them in more, some of the instruments in more detail a little later. But you can take this, put it into this instrument, press a button, and kind of the instrument will get a spectrum of this sort, and then you can have a library of for different kind of chemicals. There are databases available. For example, the Koblenz Society, one of the things it does is it has compiled a list of about 128,000 or more. In fact, now it is more than that, like sort of different chemicals. It has identified the spectrum of all these ones and characterized them like quantitatively and put them in as a database. And you can have software which takes the new unknown spectrum, does a library match, takes them and matches it to one of the kind of spectrum, one or more of these compounds. So you could match them, and that way you can find out what chemical the unknown chemical was. Similarly, people in chemistry who have made a new kind of molecule in the lab, or who have some white powder which they don't know what it is, they can put it in this instrument, like do this spectroscopy and figure out what this chemical composition is. Okay, and later on you will see that in biological samples, it's not just one chemical but a mixture of multiple chemicals. In that case, you can kind of use some machine learning or some other methods to use the spectrum and kind of identify the molecular composition which can correspond to disease, for example. So that's really how this absorption measurements could be useful. We'll get to a little bit of more about that later, but this is just as long as you understand this, this is crucial to understand the rest of it. And another phenomenon where light matter interaction happens is the process of diffraction. We saw a little bit of this in the previous class as well. So if you have light incident and say there is a hole which is a circular hole cut out, then light travels and it diffracts, and you will see not just a hole in here, but you will see like rings, a set of concentric rings in the on the plane farther away. And we saw that in fact there is like a Fourier transform relationship between these kind of these the object in this particular hole here. And so there are a few caveats. When so if you have like, when does diffraction matter? When do you think diffraction is important enough for us to worry about? Do you see this all the time? Like, let's say I take like a visiting card or a credit card size card, cut like 1 inch, like the size of a coin, kind of a hole in it, and you shine light from one side and put like a paper on the other side. Will you see a diffraction pattern? Yes, no, maybe. What do you think and why? Go ahead, both of you can. Yeah. Okay. And what about you? What do you think? Sorry? It's okay. Yeah. Okay. Anyone else wants to? Yes? Yeah. Yes. So yeah, all of you have are generally on the right track. So basically, if the hole is of the order of this, roughly the size of the wavelength of light, approximately, then the diffraction pattern will be very clear. If the hole is big, there is still diffraction going on, but it only affects us at the edges. And if you just use a magnifying glass and just look very carefully, then you will observe it. Otherwise, it will just like, to first order from far away, it just looks just like a circle. But if you look closely at the edges, and only there do you actually observe. So in general, the rule of thumb is for diffraction, if like, you need to worry about diffraction only if you're interested in objects which are approximately the size of the wavelength of light. So if you use short wavelength light, then you will have to worry about like diffraction will be a problem if like for the same object, if you use a much longer wavelength of light, you will probably have to worry about diffraction. For shorter wavelength, it may be much larger, and therefore you may not need to worry. So it's a relative, like, you can't say the objects of say 1 micron you have to worry, or that's a too general of a statement. You have to look at the wavelength of light in comparison to the size of the object, and that's really what matters in terms of whether or not diffraction always occurs. The question is it important to a particular measurement? And the answer is, if it is close to the wavelength of light, the object size is close to the wavelength of light, then it makes a big difference and you have to worry about it. Otherwise, you may not need to worry. Okay? Yeah. So whatever I'm saying is true for all wavelengths of the electromagnetic spectrum. So the electromagnetic waves can be like sort of, in fact, kilometers in size to meters in size to millimeters to microns to even kind of much shorter, kind of nanometers, which are X-rays, are in the order of nanometers and so on. So you have electromagnetic rays, electromagnetic waves across the entire like electromagnetic spectrum. There are all kinds of waves, and this is true like whatever phenomena we are talking about. When we typically talk about optics, we are talking about far IR, mid IR, near IR, visible, and UV, and so on. Okay, this is typically what comes under optics. But as Maxwell showed, light is an electromagnetic wave, and therefore everything here, it can be thought of as one general entity. Although then you make a distinction between optics and electromagnetics, they're essentially kind of what you learn in one can in many ways be applied to the other in a lot of situations. And the other thing is, although we are talking in terms of scalars, meaning at every point the field has some value, it's actually a vector. So there is an electric field and a magnetic field, and these are Maxwell's equations, and the electric field and the magnetic field at any given point has is a vectorial value, and it has each one has different directions, like, and if in air, for example, the electric and magnetic field will be perpendicular to each other. In some other media, it's possible that the electric and magnetic field are not perpendicular to each other, and so in these kind of situations, what happens is that we can use like every so for example, along if you just look at Ex, so it may have one particular, the electric field along the x-axis is traveling along the z-axis, then this is the equation, and magnetic field which is along y traveling, this is the equation. So this is just for one of the Ex is one component of the vector. So you could have all three components, Ex, Ey, Ez, and each of them could be traveling. You can write these kind of equations, and sometimes they're coupled, sometimes they're independent. So you can just keep in mind that we are dealing with vectorial kind of vectors. Although we are developing a theory for scalars, so it's a vector, and so this is where kind of the degree of complexity. So we use ray optics, right, in many situations. If for diffraction, you cannot use ray optics, so you have to use wave optics. So in most cases, you can use wave optics, and it's enough. In some special situations, you may also have to consider the vector direction, vector field. It's one extra additional degree of complexity you have to worry about. Say, when do you need to worry about this? So if, say, a material has polarization properties, it's so if it is, say, a crystal of some sort where light of X polarization goes through, it behaves in one way. If you send Y polarization, it behaves in different way. For example, the refractive index for X direction could be different than the refractive index in Y direction. If you have that kind of a material, what's called an anisotropic material, or something which has polarization properties, then you have to use the vector electromagnetic fields to study them. But if it is something which does not have these kind of properties, which is not sensitive to polarization, then you just use the scalar field and everything that you do will be correct. Okay, so only when you have complicated materials which have this kind of special properties which are related to polarization, you have to worry about the vector fields. Otherwise, the scalar field is enough. So use the kind of model which is easiest to use. I mentioned this in an earlier lecture. Make everything as simple as possible, but no simpler. So use the simplest model which works for that particular kind of an object. So you don't need to worry about the quantum mechanical or quantum optical kind of phenomena. Your electric vector field may be enough if you have polarization in most situations. Okay, so in some other special situation, you may need, that may not be enough, and which we'll get to it a little later. So the next kind of thing I wanted to tell you is about how do you quantify absorption, and how does the kind of absorption come into the picture. So here is kind of so in the slide over here, I told you in general about this alpha, which is the absorption coefficient. The question is, how is this connected to the material that you are studying? What is the relationship between this alpha and the material? And there are detailed mathematical models, physics models for absorption, which people have come up with. And one is called the Drude model for this absorption. So one way to think about it is, so there are different peaks. So if you take alpha and you measure it as a function of wavelength or frequency, in this case, then basically at different wavelengths there could be a special absorption, right? So the absorption coefficient alpha as a function of frequency could have this kind of absorption peaks. So this could come about because of various reasons. One reason it could come about is because of electronic transition. This brings us to quantum nature of atoms and so on. So this is getting to quantum optics, but not quite. Like the light itself is kind of, so the atoms, as you might remember from your elementary physics. So if you have an atom, it has different electronic, it has electrons can live in different levels, right? So there are multiple levels in which an electron can live. So if electrons are at one level, if light is incident, and it could the electron absorbs that light, it could go to a higher electronic level, and that is absorption of light. So in fact, absorption is the same. That absorption of light will result in a transition of the electron from one level to the other. If it is in this level, it could go wave 2. So depending on the wavelength, at wavelength mu1, which corresponds to this peak, it could absorb and go here. At a wavelength mu2, which is here, it could absorb this wavelength and go to this transition. Wavelength, this is mu3. It could absorb this and go to this level. Importantly, it does not have, if there is no level in between, it cannot absorb a wavelength in between these two, it cannot absorb. This is the quantization property of atoms, right? So their electronic levels are not continuous, it is discrete. There can't be levels in between this level 1, let's say it's level 1, 2 and 3. There cannot be a 1.5 level or a 2.5 level. That's the quantization, that's the discretization, that's the nature of atoms. And so this is, and therefore, if wavelength of that specific electronic transition is incident, it absorbs. If a wavelength of a different, which does not correspond to that electronic transition is incident, it will not absorb. And there is like a small, it's not exactly one wavelength, there is an uncertainty because of the uncertainty principle, there is a small band, a range of wavelengths at which this absorption happens. It's not just exact one level, there is uncertainty in the energy levels. You might have studied this as well before. So basically, that's why there is a small kind of this kind of a variation. So this results in absorption. So this corresponds to electronic transition. This model is more general than that. So typically, electronic transitions happens in the visible, to some extent in the UV, some extent in the visible, to some extent in the near infrared. So depending on the energy level difference, that could be the case. As you go to longer wavelengths, the mid-infrared, for example, it is not electronic transitions, but it's molecular vibrational transitions. So instead of it being one electron moving, it could be, say, a carbon-hydrogen bond, right? Say you have a CH, okay? So let's say this is carbon, this is hydrogen, okay? The carbon-hydrogen bond could be vibrating this way. That has a certain electron, corresponds to a certain way, quantum mechanical level. Then another different, where the vibration is kind of anti-symmetric, that could have a different quantum level. Okay, there could be a transition from one level to another, which could result in basically absorption. So this basic principle of absorption could also be true for not just atomic transition, it could be vibrational transitions, the relative movement of the CH bonds or some other, any bond for that matter. Or it could be rotational transitions. The molecule has a certain rotational shape. It could change the rotation, sort of shape. It could rotate and change the shape. That is what are called rotational levels of. So there are atomic levels, there are molecular levels, then there are rotational levels, and so on. And so that could, the atomic levels are in the visible typically, and the molecular levels are in the mid-infrared, and the rotational levels are in the far mid-infrared and far infrared, or kind of or longer wavelength mid-infrared, or even longer, sort of in the far infrared, for example, to some extent. So that's basically, these are all the reasons why light could get absorbed. And so typically you write epsilon, which is the material dielectric constant, which has at a certain frequency, at a bunch of, so any one absorption peak can be given by this kind of an equation, the dielectric constant, there is an absorption at one frequency, and then if you have multiple absorption peaks, each of them could be added together as a sequence of absorption peaks. So each that term here corresponds to a different absorption peak, and therefore each of them could be kind of some a particular molecule has multiple ones of these absorption peaks, and that's the nature of most molecules that we will encounter. Any questions about all this? Yeah. Yes. Correct. That's an interesting. That's a good question. So when light is absorbed, and then first, like it could be in that state for a certain amount of time. It may be small amount of time, large amount of time. It could be, so it is not immediately emitted. Second thing is, it can be emitted in a different direction if it is emitted. Alternatively, it may not be emitted at all. It can go to one level. It may not come back to the same level. It can go to a different level. It could result in become a thermal. It goes to a higher level. In coming back, it could come back to a different level and different level and different level. So slowly, it could come back to the original state. It may not come back directly the way it came. Okay, that's therefore it can. There are multiple different ways in which it can come back, and each of them could result in a different kind of a phenomenon. The second thing is, if it comes and instantaneously, if it is emitted in a different direction, that is scattering, and we'll get to scattering next. Okay, this is the process. Like there is actual absorption, like so. There is a difference between absorption and scattering. Absorption at the emission is different from light getting scattered. We'll get to scattering next, but so the nature of this absorption is that it actually kind of changes the state of the atom or molecule, and then you have changes after that. The changes can happen. It may not be exactly the reverse of what has happened originally. In fact, often it may not be. Any other question here? I'll get to that next. Yeah, I'll get to. So let me erase some of these things for clarity. Okay. So yeah. So this is the absorption coefficient here. The refractive. So this is the imaginary part of the complex. So this is I showed you in the previous equation, right here, K equation. This is an imaginary component of the K vector. Okay, so here you can think of this. So this is the real refractive index. So the N is the refractive index, and alpha is the absorption coefficient. But they are actually one. You can put them together as N plus I alpha or N plus J alpha as one complex number. And so it's the real and imaginary parts of the refractive index. Another way to think about this absorption is as an imaginary component, one component of the refractive index. Okay, and so there is a connection, direct connection between the absorption coefficient and the refractive index. The refraction coefficient, refractive index is not the same for like all wavelengths of light. So even for glass or any material, the refractive index can change from wavelength to wavelength. It may be change may be very small. It may be like 0.1 or 0.01. A tiny change, but still from wavelength as a function of wavelength, the refractive index could be different. That's the reason why like if you shine white light through a prism, it becomes rainbow colors, because the refractive index is slightly different for red and orange and yellow and green and blue. So the reason why it is different is related to this kind of a curve. It's the refractive index curve as a function of wavelength. Okay, and so it turns out that there is a connection between where this absorption happens and the how the refractive index changes. So whenever there is a peak, there is a refractive index maxima and minima of this sort, and another peak and a maximum and minimum of this sort. And so there is a connection between the refractive index and the absorption of materials. So those are closely interlinked. In fact, they are linked by what are called Kramer-Kronig relations. So I won't go into that's a bit too complicated for today's lecture, but there is a very clear connection between the absorption coefficient, absorption spectrum, and the refractive index of any given material. And in fact, there's an equation which connects the two in a very direct way. So these are kind of related properties of materials, and we can measure by measuring the refractive index profile. You can figure out something about the absorption profile, or if you know the absorption profile, you can know something about how the refractive index changes as a function of wavelength, for example. Okay, there is the connection between these two. One refractive index at one wavelength. So at one wavelength or one frequency, you have one refractive index. Another wavelength, you have a different could have a different refractive index. No. What I'm saying is, for different values of wavelength, n can be different. Sorry? For one, yes, for the same material, you cannot say the refractive index of glasses is say 1.5. It is 1.5 at one specific wavelength. Okay? It could be 1.5001 at another wavelength and 1.52 at a different wavelength and so on. Okay? So in that sense, the refractive index, we talk in loose terms for the entire range, it's approximately 1.5. Maybe that's true, but if you want to be precise, the refractive index is actually wavelength dependent. Any other questions? Sure. What condition are you thinking of? Oh, it changes with respect to wavelength. If you make the glass and you measure it at one wavelength, it's same glass, is the same material. If you 100 pieces of glass of the same type, it'll have the same refractive index at that one wavelength. I'm not saying it's like arbitrary. It depends on the incident wavelength, yes. Yes, you make a measurement of the refractive index at any one wavelength. And for that wavelength, there is one number for the refractive index, which is a material property. It's the same, like if you use the same material, whether you do it here or whether you do it in Delhi or whether you do it in New York, it will be the exact same like measurement and you will get the same value. But it's wavelength dependent is all I'm saying. Okay. Yeah. Other questions? Okay. Let's keep going. Huh? Yeah. So it turns out that especially for biological tissue, the profile of absorption is quite important, in fact quite crucial. And so for example, there are methods, optical methods, which use the fact that absorption of light is different at different wavelengths. So if you've gone to a hospital, many of you might have seen this kind of a clip that they put on the finger, index finger, right? And that will be connected to some instrument which is beep like every 1 second or so it will keep beeping and it will tell you kind of the heart rate and things of that sort. It's called a pulse oximeter. So it actually uses that the fact that if light goes through the finger, there is a light source here and a detector here, and you make measurements at two different wavelengths, and it turns out that if the blood oxygen, it tells you how much oxygen there is in the blood, for example. It's one of the things it can measure, blood oxygen saturation. So blood absorb, like if it's oxygenated hemoglobin, it has a certain absorption profile. It's what is called oxygenated hemoglobin. It have a different absorption profile. So making measurements at two different wavelengths, you can figure out blood how much oxygen there is in the blood. If the oxygen in the blood becomes too low, then you need immediate medical attention. The nurse or the doctor should come running to make sure that the patient is okay. That's why they put that kind of a clip to keep checking. Okay, so that's one of the, so this absorption of so that's for blood hemoglobin. You can also like different types of tissue can have different absorption profiles, and you can use this fact for making instruments and making different kinds of measurements. Another thing is, most of what inside the body is water, and so the absorption of water is a crucial kind of component to biological measurements of absorption. So for example, in the like water absorbs a lot of this, absorbs or scatters UV quite a bit, and then there is a range of wavelengths where it absorbs quite less, and these are called optical windows, meaning it has that range of some range of wavelengths, there's much less absorption than in other wavelengths. So if you want to see deeper into tissue, you will want to use a range of wavelengths where there is less absorption, so that you can go deeper into the tissue. So that happens to be in the somewhere in the near infrared, where you can use kind of like use light in the near infrared range to go slightly deeper into tissue. But as you go further along into mid infrared, absorption becomes a bit more, and therefore you can't go as deeper. But of course, you can get the molecular specificity so there are different kinds of properties you can measure at different wavelengths of light. So that's why absorption is a useful thing in biological and biomedical settings. It's the same kind of thing for even atmospheric like absorption. So I mentioned once before that lot of the things which are developed for, say, satellite imagery or things of that sort are actually useful in medical imaging. So it's strange, but one is looking at much bigger scales in from satellite, so big, right? Like you're looking at how like a big part of the earth. Instruments that are developed for that are often used for imaging the microscopic scale, because the lot of problems that you'll encounter, water absorption in the atmosphere, is similar to the water absorption that you see in kind of tissue, for example, or whatever problems they have solved over there. You can learn from that and apply it to your medical. And if you have made some discoveries or inventions in the medical field, maybe you can apply it to satellite. So what I'm saying, what the point I'm trying to convey is that there is a kind of, if you make one kind of an instrument for a particular purpose, it's quite possible that it can be applied in a completely different domain. It's up to your imagination. There is a big connection between all these things. In fact, even kind of earlier, in earlier days, so a lot of the software that people built for, say, remote sensing and kind of satellite imaging was actually what software people in infrared imaging, in mid-infrared imaging used to do the data analysis, because they were kind of, they were so similar in terms of the nature of the data that you obtain. Okay? Just keep that in mind, because like if you think you are doing like, so if you want to build an instrument, don't just look at what people have done in that field, but in related fields, if you have like what other people have done, you don't need to reinvent it. You can learn from whatever they have done, adapt it, modify it in whatever way you need to, and so it's much less effort, and you can make progress, and you can make progress faster that way. Yeah. So the way you quantify this kind of absorption is using what's called Beer-Lambert law. And what this says is, let's say you have light incident and its intensity is I0 at the top of the sample which absorbs. It goes through the sample, and at the other end light coming out is I1. So take the ratio of I1 divided by I0. Okay, that will be, because it's an exponential decay, it will be e to the minus alpha d, where d is the thickness of the optical thing you are trying to study. So alpha is the absorption coefficient, d is the thickness, e to the minus alpha d is what you measure. And this alpha can also be decomposed into c and kappa. So what does that mean? It depends on the concentration and it depends on the absorption profile. Okay. So how much? So let's say there are one molecule 1 and molecule 2 and both are absorbing. Okay. So the concentration of one times the absorption profile, absorption of the first molecule, concentration of the second molecule times the absorption value of the second. So the overall absorption coefficient may not be because of just one molecule. There may be multiple molecules which are absorbing, and so the concentration times the value of the absorption constant for that one molecule. That is what you have to measure, and it's a combination of multiple molecules. This Beer-Lambert allows you to find the concentration, this absorption constant, and the distance. Okay, so all three of them, so the absorbance, the concentration, and the thickness, all three contribute to the reduction in intensity. And you can find, typically you can find the combination of the two. So you don't just find one, you find a combination of these. So sometimes it may not be possible, you cannot decouple the concentration times thickness, but that's okay. As long as you have the relative concentration of different molecules, it may be enough for most practical purposes. Or alternatively, you can like measure the thickness. Say you want to say cut the tissue into thin slices. You know that the slice thickness is 5 microns, and therefore you know d, and therefore you can figure out the absorption coefficient or the concentration times the absorbance, the kappa 1. So you can find the combination that way. If you know one, you can figure out the other by doing this kind of a measurement. Okay, this is the kind of measurement that is used in what is called FTIR, Fourier Transform Infrared, FTIR spectroscopy. Okay, so Fourier Transform Infrared spectroscopy uses this kind of a. So how do you make a measurement of I0? Just remove the sample, measure the intensity, put the sample in, measure the intensity. So I0 is without the sample, I1 is with the sample. So you can make two measurements, take the ratio, then take the log and do the calculation, and that way you can get to what the material's property is. That's essentially how these spectroscopic measurements can be done. Questions? Okay. So, absorption is also an important phenomena in X-rays. So, I was talking about atomic transitions and so on. So, X-rays is a bit different than that. So, basically, when X-rays pass through, say, the hand, then the bones preferentially absorb the X-rays relative to the other kinds of tissue. Other tissue also to absorb to some extent, but it's much less than the calcium, especially in the bone, is actually absorbs significantly, and therefore X-ray gives you a contrast based on the value of the like absorption coefficient of the bone relative to the absorption coefficient of tissue and other things. So you can look at the photon energy. How much of what is the energy in the photon, and you can create a plot of like sort of attenuation or absorption coefficient, and that tells you something about the nature of like the materials in X-ray. You can use this. You can also use X-ray absorption to kind of figure out what is the composition of the object that you're looking at, and so on. And like you can make plots of this sort and figure out yeah. So this is like this is an X-ray image where you can see through like say a truck or something of that sort, right? So you can make images of this sort and figure out things. Yeah, yeah, sure. Say that again. L edge, yeah. So the K edge, like so, these are the different kind of. There are different bumps in the like as a function of just like you have absorption profiles, you have this kind of in X-rays you have something similar, like preferential absorption at some specific photon energies. So just like you had this kind of a plot, right? So this kind of a plot is for X-rays is something looks something like this. Okay. These are X-ray, not MRI. This is for optical absorption. Yes. So these are for electronic transition states or molecular transition states, something of that kind. Say that again. No, so you can. So I won't go into the details of exactly what you can do. You can basically characterize material properties. So, for example, is it calcium or is it some other atom? Which like what you can find the atomic one possibility is that you could find the atomic composition of like what atoms are present in a particular sample. That's the kind of thing you can potentially figure out. Okay, so yeah, so um, the relative densities, relative concentrations of different atoms and so on. So yeah, coming back to uh, we'll break in just a few minutes. Okay, so coming back to the other properties of light that we can use and which is different for different materials. So the refractive index, whenever there is a change in the refractive index, there can be reflection and refraction of light, and that is an important, it's also an important material property, the refractive index. Whenever there is a change, there are several things that happen, and one is reflection, and the amount of reflection is given by the reflectance or the reflection coefficient, which is eta 1 minus eta 2, where eta is this mu naught, square root of mu naught by epsilon. Epsilon is the permittivity of the medium. Okay, so if it is air, it is epsilon naught, and that has some constant. It's called the impedance of free space. So this eta 1 and eta 2 are the impedances of this medium and this medium, which is related to the refractive index. So it's n1 minus n2 divided by n1 plus n2, which is the refractive index. Okay, so the eta is related to the refractive index of the medium, and so if n is equal to 1 for air and n is equal to say 1.5 for glass or something, then you have eta 1 and eta 2, and like so the how much light is incident on this surface, how much of it is reflected is given by, if it's perpendicular, it's given by this equation, and how much of it is transmitted is also given by, like the rest of it is transmitted essentially. So instead of, so in the previous case, the amount of light reflected from the surface is given by this relative like the value of the light that comes back is given by this particular expression here, and the rest, so because of conservation of energy, light is either reflected or transmitted. So if it is reflected, this is the value of the reflection coefficient or reflectance. If it is like the rest of it is transmitted. Okay, so that's how you can think about this. So instead of it being incident perpendicular to the surface, if it is incident at a small angle, then what? Right? So if it is incident in a with a direction vector k1, then there will be a reflected wave. So some amount of it is reflected, some amount of it is transmitted. And so if you want to figure out how much is reflected and how much is transmitted, there is an equation which tells you that the reflection corresponds to like cosine or secant theta, which is 1 over cosine theta. So this is the expression. If you kind of rearrange these terms, you will get something of this sort. So basically, so this is the more general. So if theta 1 is the incidence angle, then you can know how much of it is light is reflected, how much of it is transmitted. So how much of it is transmitted is given by this value over here. Okay. So this is I'm not going to derive this into this class. That's for a different. You might have seen it in your electromagnetics course or some other course. But basically, the important thing is these phenomena happen, and we could use them for like building something, for example. And if so, this is for scalar, like typically for scalar fields. But if you have vector field, then the electric field vector, for example, could be perpendicular, like coming this way, right? So it will the electric field could be coming this way, and so the electric field is like this. It is in, and this is the surface. It's incident like this and gets reflected. So that's this case. And if it is electric field is like this, it's coming like this, and when it gets reflected, it goes like this. So that's this situation. And so for longitudinal waves, like sound waves, this is the third kind of situation. But for electric and magnetic fields, typically you have electric field being like this, or electric field coming like this and going like this. So this is what's called the TE polarization, transverse electric. Electric field is in this direction, and transverse magnetic. The magnetic field is this way, and the electric field is perpendicular like this, and then like this. So that's those are the two typical situations. And if you want to, if in the model of light that you use, if it is vectorial, then you will have to use TE and TM, transverse electric and transverse magnetic polarization, and do your calculations. If you can use scalar fields, and if it's enough for your calculation, then use that and don't worry about the vector version of things. So that's my general advice to you, is use the simplest model of light that is sufficient for the everything that you're studying. If you unnecessarily complicate things, then like calculations become more like difficult. You're doing unnecessary work. Okay. So this was for one layer. You could have multiple layers, and one way to deal with it is this light goes through, some of it is reflected. Now what happens is it goes through here, it transmits. There could be a second reflection here, and it goes through, and it could be a second reflection and another reflection, it goes through. So basically they could have multiple reflections at all these, and light coming here, go through and transmit. It comes back. So there are so many of these multiple situations that can happen, right? So you can set up boundary conditions, and so there's an infinite series. It keeps bouncing back and forth, and after you solve for this infinite series, the infinite series will have a finite sum, and in the end you will have an expression of this sort, where the transmission for like here 1 to 2, 1 to 3, like how much light goes completely through and how much of it comes back, and so on. Transition from 1 to 2, how much is there light gets reflected and transmitted, and so on. So all these kind of at the boundary between 1 and 2, how much is reflected from between 1 and like how much is transmitted at 1 and 2, and so on. So each of these reflection coefficients. So what I'm saying is, if some amount of light is incident, after all this happens, some amount is reflected overall, after all multiple reflections and everything, some amount is transmitted, and some amount of it goes through. So there are people have figured out the kind of figure out all this and come up with expressions which tell you exactly how much goes through and how much comes back. And this is a wavelength dependent phenomenon. And the reason, one of the practical uses of this is in what is called anti-reflection coating. Okay, so when you're doing experiments with optics, so whenever you have say a lens, light falls on the lens, and small amount of it reflects back. Just because, in fact, why does that happen? It's because if refractive index of air is 1 and glass is 1.5, this 1.5 minus 1 divided by 1 so there is some reflection coefficient, right? This is not 0. So some amount of it light reflects back. And so because of that kind of a reflection, so you lose, like, the amount of light that goes through the lens is not 100%. So that's a problem, right? If you want to build an efficient system where, like, so every time you pass it through a lens, some amount of light is lost. So you keep losing light, and so your system becomes inefficient. So how do you build a better system? So you can put a coating, some kind of a coating on the lens, what is called anti-reflection coating, where such that after all these multiple reflections, what happens is that the transmission, if you optimize it such that the transmission is near almost 100% and the reflection is 0%. So for a certain range of wavelengths, so you can't make it for all possible wavelengths, but for a small range of wavelengths, you can put a coating of thickness D such that the transmission coefficient is 100% and reflection coefficient is 0%. And that way you can kind of build very efficient systems. So in fact, people, like today, you don't even need to do it yourself. You can buy components, lenses. When you buy a lens, if you can have an anti-reflection coating on it already, and but you have to choose the disadvantages. Yeah, like it can't be for all possible wavelengths. You have to choose the range of wavelengths for which this anti-reflection coating works. For other wavelengths, it will actually perform worse. So if, say, for example, 600 to 700 nanometers, there is anti-reflection coating. If you use it for 400 nanometer light, then it may actually reflect a lot more. It may be inefficient for other wavelengths, but it will be highly efficient for 600 to 700 nanometer light. So basically, you have to be careful in choosing what coating you will use, so that the system is overall efficient. You don't want to lose too much light as light goes through the system. But this is one way of making efficient kind of optics. Let me stop here for now. Take a break. We'll get back. Okay.